YOLO, or you only look once, for object detection. So today we'll deal about this YOLO and how it works. What are the challenges and limitations in this, its architecture and its implementation using OpenCV. So this you only look once architecture was first published in 2016. At the time, previous methods for object detection like RCNN and its variations, they used a pipeline to perform this task in multiple steps. And this can be slow to run and also hard to optimize because each individual components must be trained separately. And in case of YOLO, the name itself explains a lot about it. That is, it just goes through the entire image just once. So today we will explore how YOLO works. So let's first understand how YOLO encodes its output. So here this input image is divided into n grid cell, and for each object which is present in the image, one grid cell is responsible for predicting the object. Each grid will predict the B bounding boxes and C class probabilities. And the bounding box consists of 5 components. That is X and Y coordinates, which is representing the center of box, width and height of this box, what is the width and height, and finally the confidence, which is representing whether that object exists or not exists in this image. The cell which has the center of object, that cell determines or is responsible for detecting objects. Now, there must be certain challenges in YOLO. So, how do we tell if the object detection algorithm is working fine or not? So, the solution is this intersection over union, which is calculated using this size of yellow part and the size of blue part, right? That is area of intersection by area of union. So if this intersection over union is greater than 0.5, we consider the algorithm is working fine, else we need to do the part again. Then the second challenge can be that there can be multiple bounding boxes for each object. So how to deal with this? So here the solution is non-maximal suppression. So which is the way to make sure that your algorithm detects your object only once. So because you are running image classification and localization algorithm on every grid cell, so it is possible that many of the cells says that their PC or the class probability or the chance of having object in that cell is highest. So when we run this algorithm, we might end up with multiple detections for same object. So what this non-maximal suppression does is that it cleans up other unwanted detections. So we just end up with one detection for particular object. So how does this non-maximal suppression work? First, it looks for the probabilities associated with each of this detection for particular object. It takes the largest PC, which is the most confident detection for the object. Having done that, the non-maximal suppression part looks for all remaining boundary boxes and chooses all those bounding boxes which has highest intersection over union with the bounding box of highest PC and suppress them. Then we look for remaining bounding box and find largest PC, and again NMS looks for remaining bounding box which is highest IOU with bounding box of high PC, and then they will get suppressed. So by doing this for every object, we get only one bounding box for each object. So see for this example. So here we have taken the 0.9 in this case. Like in the previous example, so we will consider that it has the highest probability. The third challenge is, what if we have multiple objects in a single cell? That is, what if we have overlapping objects and midpoint of both objects lie in single grid? So in this case, we will use multiple anchor boxes for solving this. Here each cell represents the output like P, C, X, Y, H, W, C1, C2, C3, which is a vector of shape 8 by n, that is 8 rows and 1 columns, right? C1, C2, C3, these are the different classes, say person, car, bike. So the shape of bounding box can change depending on the number of classes. Now each cell won't be able to output 2 detections, so we have to pick any one of the 2 detections to output. So with the idea of this anchor box is that what you are going to do is to predefine two different shapes called anchor box 1, anchor box 2. So by doing this, we can do two predictions with two anchor boxes. So in general, we can use more anchor boxes to capture variety of shapes the object has. So for two anchor box, how our output will be in the case of three classes. So at the time, the output should be a vector of size 16, 1, and the vector contain PC, X1, Y1, H1, W1, C1, C2, C3 like this. Another can be the PC2, X2, Y2, H2, W2, C1, C2, C3. Why I'm saying C1, C2, C3? Like if there are three things, we are checking for the person, car and bike. And we are just checking the XY coordinates and width and height and whether the object has or not, right? So combining all these steps, we get our YOLO, right? Here we are getting this YOLO 5x5 grid, we are having this bounding box plus we are having the confidence and then we are getting the final detection. But there must be certain limitations of this YOLO. That is key. First limitation is YOLO can only predict a limited number of bounding boxes per grid cell, 2 in the original research paper. And though that number can be increased, only one class prediction can be made per cell. So which limits the detection when multiple objects appear in a single grid cell. So thus it struggles with bounding groups of small objects such as flock of birds or multiple small objects of different classes. Now, what's the architecture of YOLO? So we will discuss the architecture of YOLO V3, which uses a variant of DarkNet, which originally has 53 layer network trained on ImageNet. So for the task of detection, 53 more layers are stacked onto it, which gives us a 106 layer fully convolutional underlying architecture for YOLO V3, and the detections are made at 3 layers, 82, 94 and 106 layers. So the convolutional layers in YOLO, basically it contains 53 convolution layers, each followed by batch normalization and leaky ReLU activation. And this convolutional layer is used to convolve multiple filters on the images and produce multiple feature maps. And no form of pulling is used, and a convolution layer with stride 2 is used to downsample the feature maps, and it helps in preventing the loss of low-level features often attributed to pulling. So now let's look at the input. How does it look like? Now input is a batch of N41641663, right? Where N is the number of images and 416416 is a width and height and 3 is the number of channels. So width and the height can be changed to any number which is divisible by 32. So why divisible by 32? So we'll see that in this moment, if we increase the resolution of image or the input, it might increase the accuracy after training. So this input images can be of any size. We don't need to resize them before feeding them to the network. They all will be resized according to input network size. So how does this network detect the object? YOLO V3, it makes the detections at 3 different places in the network. These are the layers 82, 94 and 106. And these numbers are called strides to the network. And they show that how the output at 3 places in the network are smaller than network input. So for this network input 416 into 416. For 82nd layer, the stride is 32 and the output is 13 into 13. And it's responsible to detect large objects. For 94th layer, the stride is 16. The output size is 26 into 26 and it's responsible to detect medium objects. For 106th layer, the stride is 8 and it's responsible to detect small objects. This is the reason why the network input must be divisible by 32. Because if it is divisible by 32, then it is also divisible by 16 and 8 as well. So these are just a prediction feature maps at the different scales. So now let us see what detection kernels are. So basically to produce these outputs, YOLO V3 applies 1:1 kernels or the filters at 3 output layers in the network. And this 1:1 kernels are applied to downsample images so that our output has same special dimensions, that is 13 into 13, 26 into 26 and 52 into 52. Now the shape of this detection kernels also has its width, that is calculated by this formula, that is B into 5 plus 6. B is the number of bounding boxes, C is the number of classes and 80 is the YOLO data COCO data set. So each bounding box has 5 plus C attributes. So for YOLO V3 it predicts 3 bounding boxes for every cell. So B is 3 here. So now we can say each feature maps which is produced by this detection kernel at 3 separate places. Output layers in the network has only 1 dimension depth that incorporates this 255 attributes of bounding box for COCO dataset, right? So let us now understand the grid cells. So grid cells are basically the detection cells. We already know that YOLO V3 predicts 3 bounding box for every cell of feature maps. So what is the task of YOLO V3 is identify the cell which contains the center of objects and training the YOLO V3. So when it is training, it has one grounding truth bounding box which is responsible for detection of one object. So we need to know which cell this bounding boxes belongs to. So for this, YOLO V3 makes prediction at 3 scales for strides 32, 16 and 8. So the cell which has center of the object is responsible for detecting the object. Now anchor boxes are used to predict bounding boxes. YOLO V3 uses the predefined bounding box called as anchors, and also these anchors are used to calculate real width and real height for predicted bounding box. So in total 9 anchor boxes are used, 3 anchor boxes for each scale and 3 biggest anchors for first scale, the next 3 for second scale, the next 3 for third scale. This means that each output layer for every grid scale can predict 3 bounding boxes using 3 anchor boxes. So for calculating this, we use the k-means clustering algorithm. And to predict this real height and width of this bounding box, YOLO V3 calculates the offsets, also called as log space transform. So to predict center coordinates of this bounding box, that is Bx and By, YOLO V3 passes this output Tx and Ty through sigmoid function. So based on this equation given in this figure, we can see the central coordinates and width and height of these bounding boxes. And all this redundant bounding box from 10,847 boxes, these are suppressed using non-maximal suppression. So how do we implement this YOLO V3 for object detection? So here we will take the OpenCV library. So first we will import the required libraries, right? So as shown in the line 6 here, we will use this command cv.d and n.readnet to read our weights file and configuration files. That weight files means which contains the pre-trained weights which has been trained on COCO dataset, and the CFG file is known as configuration file which has this YOLO V3 network architecture. Now this line 8 and 9, here we store the confidence threshold and this non-maximal suppression threshold as constant. And this line 11 to 13, it will read the coco.name file to extract the object names and put it in the list so that we have 80 classes in total. Now this 16th line, it shows that cv.video capture, right? So we read our video here. Now here in the line 18, we will loop over to read the captured video and do the object detection task. And this line 19, now this cap.read is reading the video and it will be read as the frames, and this function returns two outputs. Basically first is the Boolean function, that is true or false, right? And the second one is where the frames. Now line 23. So here we cannot pass the frames directly to our network. So we need to normalize the frames. Also we need to resize the frames to 416 as 416 because YOLO V3 takes this input and OpenCV reads image in BGR format. So we need to swap blue and red channels as well and then pass the frames to the network. Now this line 26 and 27. So here we also need to get output layers name and pass the names in forward pass, right? But we are not done here, as we need to visualize the results. For that we need to extract bounding box, with what confidence we predict the object, what class is the object. So here the line 34 to 35, we use two for loops to extract bounding box, confidence and class IDs. Line 35 to 37, right? Here the detections contain 85 parameters for each object detected, where first 5 parameters are bounding box and confidence, and after that we have probability for prediction of AT class. So first loop takes each one output layer from this 3 output layers in total, and in second loop we will find the detected object in each output layers. Now this lines 38 to 49. So it's based on this confidence threshold. So here we extract the center of bounding box and its width and height and append them in the empty list which we have created. And this line 44 to 45. So we are extracting the top left coordinates of this bounding box. Now we have got all the bounding boxes, but we need only one bounding box each object. So we pass the bounding box to non-maximal suppression function from this open CV. So here this line 51, it's based on the confidence threshold and NMS threshold or the non-maximal suppression threshold. The boxes will get suppressed and we will get the box which detects the object correctly. Now this lines 52 to 58. So here we are just fetching the required coordinates for the bounding boxes and its confidence and label and assigning a color to it. Now line 60 to 61. So here we are drawing the rectangle bounding box for this objects detected and putting the text above that bounding box. Right? So here we have shown this detected objects using this line. Okay, using cv.im show. So hope you have understood the YOLO V3 architecture for object detection. Thank you.